So in our previous Chapter 4 videos, we've discussed vapor pressure and what it is. And now we're going to delve into the specifics of vapor pressure for meteorology a bit more. Remember, this is vapor pressure for meteorology. It's a combination of chemistry, which has a different definition, plus physics, plus biology. So in looking at vapor pressure, I hope you stay with me on these videos, because if you go to YouTube and look up vapor pressure, you're going to get the chemistry definition. It's going to be a bit different. It's going to confuse you in regard to what we're looking for. What we're looking for is the pressure of water vapor in the atmosphere. And the pressure of water vapor in the atmosphere is known as a partial pressure because it is one component of the atmosphere, and the other components can include nitrogen molecules and oxygen molecules and carbon dioxide molecules and argon molecules. And all of those molecules can be part of a model parcel of air, an imaginary parcel of air, an air mass, you might say. And in this air mass, which has many different kinds of molecules, the water vapor is one of the types of molecules that is exerting force on the surface of the parcel, so that the water vapor has a partial pressure to the air pressure. And we call this the vapor pressure, this partial pressure. Now, we in this video are going to look into different types of water vapor pressure. And there are different types of water vapor pressure in the entire atmosphere. And then we can go very specifically onto a water surface. So let's start with the big one, the type of vapor pressure that we see in the atmosphere. So let's talk about the entire atmosphere as being about 1,000 millibars of nitrogen and oxygen and water vapor and carbon dioxide and argon and everything else. About 1,000 millibars of atmospheric sea level pressure. Of that 1,000 millibars of atmospheric sea level pressure, there's a small fraction of vapor pressure. In fact, if you're in a desert where there's not very much water vapor, that's going to be roughly 10 millibars of 1,000 millibars of atmospheric sea level pressure, about 1%. And if you are in a rainforest in Bangkok or in Thailand, like your chapter opens with a paragraph on that, you might find that at maximum there's 40 millibars of vapor pressure of the 1,000 millibars of atmospheric sea level pressure. That's 4%. And yet you now know of the energy that this vapor pressure brings to that atmosphere and the importance of those small fractional measurements there. So this is what we call atmospheric vapor pressure. We also call it actual vapor pressure. So you can think of the two A's. Atmospheric vapor pressure is actual vapor pressure, and we're going to be using the term actual vapor pressure. And when we think about this, we think about the fact that this actual vapor pressure is entirely dependent on water vapor levels in the atmosphere. And in the desert, there is really not much water vapor in the atmosphere. And in the rainforest, there's a lot more, 4 times more water vapor in the atmosphere. So this actual vapor pressure is entirely dependent on the amount of evaporated water in the atmosphere. It's really the only thing that impacts that measurement. There is a second type of water vapor pressure, and it's a more specific type of water vapor pressure. In fact, of the 10 to 40 millibars of atmospheric actual vapor pressure, there is a vapor pressure measurement, and it's easiest to measure this on a water surface. So a water surface is part of the atmosphere, but it's a very specific part of the atmosphere. There's a vapor pressure on a water surface where the number of molecules leaving equals the number of molecules returning at equilibrium. There is an equilibrium vapor pressure at a water surface where the phases are changing between water and vapor. We call this specific water vapor pressure the saturation vapor pressure. So it's going to be between 10 and 40 millibars of the actual atmospheric vapor pressure. But this is going to be a specific one that is usually measured on the water surface because that's such an easy place to get an equilibrium vapor pressure. An equilibrium vapor pressure is saturated air right here where the number of molecules leaving equals the number of molecules returning. We call that a saturation vapor pressure. So now you know vapor pressure, the umbrella, and two different types, a broad type called actual vapor pressure, which is atmospheric vapor pressure between 10 and 40 millibars, and a really specific type in the atmosphere, which is on a water surface, and that is showing an equilibrium vapor pressure called saturation vapor pressure. If we look at saturation vapor pressure a little bit more deeply, we see that saturation vapor pressure, that equilibrium vapor pressure at the water surface, is entirely dependent on temperature. Because, for instance, if we put a cover on cold water, let's say this wasn't room temperature water, let's say it was cold water, you know that you wouldn't get much energy out of this water to allow the kinetic energy needed to produce a lot of vapor in this setup with cold water. You know that you wouldn't get a lot of vapor there. But you know that if it was room temperature water, you would get more vapor. You would not see this vapor because it is invisible, remember. But you know that you have vapor in that area, in that room temperature water, because in a day or two, that water would evaporate in a dry room. And let's say this was hot water. Let's say this was hot tea. You know that you would get more vapor up here because you would actually see condensation from so much vapor in that atmosphere. So you know that saturation vapor pressure is entirely due to temperature here. And when we think about that, we can graph it. And we can graph this saturation vapor pressure directly dependent on temperature. In fact, we can put temperature on the x-axis here, and we can put vapor pressure on the y-axis. Now, you know, like I mentioned before, that if we had ice in iced tea, we would get a little bit of vapor. Maybe in 3 or 4 days it might evaporate. But if we put hot tea in there, you would get a lot of vapor off. In fact, you would see the condensed vapor as steam in a little puff above that. So you know by observation, you know that this equilibrium vapor pressure is going to be higher when temperature increases. Temperature increases down here. We see our saturation vapor pressure line in red go higher here. So the way to read this is to say, let's take our independent variable of temperature on the x-axis and look up at 10 degrees Celsius. 10 degrees Celsius is rather chilly, and for that water, that would put out about 12 millibars of vapor pressure. And that would be not a lot of vapor pressure, a pretty dry environment. Remember, the desert was at 10 millibars of vapor pressure. This is a pretty dry environment here. But if we went to 32 or so degrees Celsius, which is right around 100 degrees Fahrenheit, you would find that the equilibrium pressure of all the vapor coming off and all the vapor condensing back down is much higher at about 38 millibars. So that is why you can have rainforests at the tropics with really high temperatures around 100 degrees Fahrenheit, and you can have rainforests with a lot of water vapor in the air very, very humid, at about 38 millibars. The thing to take home here is that saturation vapor pressure at the surface of water, the vapor pressure of the water molecules leaving as vapor, and the vapor pressure of returning as water, that equilibrium pressure is entirely dependent on temperature. This graph shows that. The way to use this graph is to go from the x-axis, go up to the saturation vapor pressure line in red, and then read over to the y-axis to get your vapor pressure measurement. I will see you on the next video.